Well, it's a great pleasure to be here, and I'm sorry not to be with you, and I'm also sorry that I couldn't hear more of the excellent courses in the during the week. But I also am very conscious that it's been a very intense time, and I hope that uh, this material will be straightforward and perhaps easy to discuss. And of course, it will echo very closely some of the non-technical aspects of Sebastian de Haro's lectures during the week. So this is very much as I have been instructed by Sebastian over the years, and the material I'm going to tell you about is really some parts of those three papers that are listed. The other papers in brackets are the papers that Sebas wrote with Jeroen van Dongen and Manus Visser about black hole entropy. So it's a bit like the last talk. So the plan will really have 4 parts with maybe a 5th. There's some material at the end that is not announced here because I think we won't get to it. I'd like to just remind you of how Sebastian and I think about dualities, what we call a schema for describing them. Then I want to discuss a philosophy topic about how 2 dual theories can differ. Then I want to give you 3 simple examples about that. And finally, I'd like to talk about emergence in relation to the schema, again, using those simple examples. And although emergence is a very controversial topic with many different meanings, I'll only really make a simple set of comments about it. So number 1 immediately then is that Sebastian and I take a duality to be a matter of 2 dual theories having a common core, which is called the Baire theory. And the 2 theories are instantiations of the Baire theory, or representations of it, or realizations of it in the sense of representation theory, which really means that there might be a not injective map. It's homomorphism rather than isomorphism. But when you go down to the level of these 2 representations, the one is isomorphic to the other. So there's a physical theory would normally have a set of states, a set of quantities, and a dynamics, curly S, curly Q, curly D. And you can think of the theories as a triple of those. So we'll use the phrase model triple, because the dual theories will be labeled by us as models. We're going to mostly associate the word theory with the Baire theory at the top, and mostly associate the word model with the 2 things which enjoy the duality one to another. Okay, in the second topic, I'm going to invoke what is called intentional semantics by logicians, so as to sort out different ways that 2 dual theories can be different. They can contradict each other about a common topic, or they can describe different but isomorphic subject matters. And then when I come to my examples, the examples will be very simple. They're going to, in fact, be 2 examples in Newtonian mechanics, an example in quantum mechanics with position and momentum duality, and there's the Kramers-Vanier duality in statistical mechanics. And we can already see that these 3 examples illustrate different meanings of the word difference, right? In Little Roman 1, the two duals contradict each other. But in Little Roman 2, the duals are usually taken as describing the same physics, though in surprisingly different terms. You ask, in elementary quantum mechanics, you have the wave function. You take its Fourier transform to get a different mathematical function, but it represents the same physical situation, the one in terms of position, the other in terms of momentum, but it's the same physical situation being described. And on the other hand, in the final example, the duals describe different physics from one another. There's a lattice system like graph paper, but one is hot and the other is cold. They're different, but their behavior is in a certain respect isomorphic. So that's my main story. The fourth chapter or part will be about emergence, where I'll be reporting in a slide what De Haro has said about emergence and illustrating it with the examples from Newtonian mechanics and from quantum mechanics. Okay, so the result of all this is that there will be these sections. I'm going to introduce dualities, going to then say what is the schema. Then I'm going to talk about this logician and philosopher's framework of intentional semantics. Then I'm going to talk about the three examples. And I've got a philosophy implication about that, about this topic of when are two theories the same. Then I'll talk about emergence, and maybe we'll talk about symmetries in relation to dualities in section 7 and 8. But I suspect better to have a discussion. Okay, so here's the introduction in terms of 3 comments. As I said, and as Seb said, a bare theory can be realized or modeled in various ways, rather like representation theory. In general, 2 models are not isomorphic, but when they are isomorphic, we say there is a duality. And these isomorphic theories will be called model triples. And so our word model rejects 3 connotations which you might have in your mind with the word model. One connotation that is often around is that a theory is general, but a model is a specific solution for the physical system concerned. Another connotation that is often around is that a model is approximate, whereas a theory is exact. And a third connotation is that a theory is never a part of the world. A theory is something that gets interpreted in using the world or by bits of the world, but a model might be part of the physical world. So those are 3 traditional connotations, and please bear in mind that our use of model rejects all of those. Okay, so that's a little warning about the words. There is something that Sebastian stressed, that discovering a duality is normally done in the context of studying not the bare theory, but 2 interpreted models of such a theory. And the scientific interest is partly that we don't initially believe them to be isomorphic in any relevant respect. We don't believe them perhaps to be models of any single relevant theory. And then we discover, to our surprise, that they are. Okay, so there's notation for this. A model M, which is going to be one of these dual theories, is realizing a theory T. When it does so, it has specific structure of its own. If you think of an abstract group and its representation by collections of matrices. That's a good example. Clearly, there is specific structure in a matrix or in a collection of matrices. Are they 5 by 5 matrices or 3 by 3? Are they over the real numbers or the complex numbers? Those aspects, specific structure, are not in the abstract group of which they are a representation. So it'll be helpful to have a notation for the specific structure, but the specific structure is like building blocks. You build the representation using the ingredients or the building blocks given by the specific structure. But the part, so to speak, of the result, which does the representing, is the model root. But you probably couldn't define a function on the model root itself without mentioning the specific structure, because it's right in there. It's part of the mathematical object concerned. So the model as a whole is appropriately divided intuitively into the part that is doing the representing and the specific structure. And the part that is doing the representing is little m, or called the model triple, or the model root. And the other notation for it is t sub m, because by mentioning t, you signal that you are thinking of it as representing the bare theory T. So now it's easy to say what a duality is. There are two model triples, that they have their model roots, and there is a duality between the model roots, or rather a duality between the two models is an isomorphism between the model roots. And what is a model root isomorphism? Well, first of all, there are the states. And so you need to have an isomorphism of the one state space with the other state space. And you imagine that there is an isomorphism between the sets of quantities of the two models. And these isomorphisms aren't just any isomorphisms, they have to make the values match, where I'm using angle bracket for the value of. So I wonder if you can see my cursor. This expression means the value in the left or number one model of the quantity Q1 in the state S1. And that's to be equal to the value over on the right-hand side in model 2 of the corresponding quantity in the corresponding state. Also, these isomorphisms, dq and ds, must respect dynamics. And in elementary quantum theory, we learned that you can think of quantum as dynamics in terms of either Schrödinger or Heisenberg. That contrast is easily seen to be valid also for classical mechanics, and what a mathematician would call equivariance of one map with respect to another is shown in this figure. The two duals are organized in my mind always on left and right, one on the left, two on the right. And the state spaces are on the left diagram, the quantities are on the right diagram, and the dynamics is the downward arrows here. So ds is to be equivariant for the dynamics of the two theories, if you were to adopt the Schrödinger picture of dynamics that states change over time, and similarly in the Heisenberg picture. Okay, so this is echoing Sebastian earlier in the week. I'm going to move to my second main chapter, which is this section about intentional semantics. My section titles are at the top of the slides, and the section we're in is normally more vivid, a darker red. So the first comment is, so to speak, an apology to physicists or an explanation. Philosophers and logicians are very obsessed by the word same and different, because same and different are used in different meanings very flexibly, and it can be confusing trying to keep track of exactly what counts as the same and what makes a difference in the relevant sense. Similarly, the words equivalent and inequivalent. And corresponding to this variety, there is also variety of how many possibilities are there in this discussion. The more discriminating we are, the more fine-grained we are, the more we distinguish and count things as different, the more possibilities there will be. If we have a reduced focus and we don't count so many differences, there will be fewer possibilities. So philosophers will know the names of Frege, Carnap, and Lewis, and over that century from Frege to Lewis, there evolved what has come to be called intentional semantics. And it is an adaptation of ideas of Frege to the logic of possibility and necessity, which was spearheaded by Carnap and brought to a high level of detail by Lewis and by Montague. And indeed, this framework is called Montague grammar by linguists. So the idea is that there is a set of ways the world could be. They're called capital W. Each way the world could be is a possible world. And a referring term like this particle, this lattice, is going to be assigned as what Frege would call a referent or Bedeutung, an object. But it is assigned this referent relative to each world, which would include the actual world. And so the standard example might be the capital of Denmark. It is a referring expression. It refers to Copenhagen, but it might have referred to Aarhus. So that is construed in this framework as there is a possible world in which what we call Aarhus is the capital of Denmark instead of what we call Copenhagen. And perhaps in such a world, they speak the same language in Denmark and in England as we do in the actual world. And so even in their language, they say that the capital of Denmark is Aarhus. So the general idea is that a referring expression can have a referent that changes with different circumstances. And the same goes for a predicate, such as has momentum P or is hot. It has a certain set of instances, but what is the set of instances will vary according to how the world is. And in the same way, the truth value, true or false, of a sentence varies according to how the world is. And in the jargon, the referent of a referring term, or the set of instances of a predicate, or the truth value, true or false, of a sentence, they're all of them called extensions. But the meaning of a piece of language is really the thing you have in your head. It's not a piece of the world or a piece of a possible world or a set of items in a possible world. That is not the kind of meaning you have in your head. What you have in your head is an assignment or a function or a map, which sends a world, little w, to that piece of language's extension at w. So that's called the item's intention. So this is what Frege called Sinn, or what we translate into English as sense. The sense of the predicate is the assignment to each world of its set of instances in that world. Okay, so that's summarized at the top. A word or a sentence is assigned an intension as its meaning, a map from sets of worlds, W, to extensions. And then I make a joke. I mean, this framework has the great merit that it respects the meanings of words. In my examples, I used Copenhagen, Denmark capital in the ordinary English sense. I did not assign an egg to the word Denmark. I did not assign Donald Trump and my left arm as the extension of the predicate is a capital. Well, that's what you would expect of semantics. It's meant to be respecting the meanings of words. But I'd like to tell the physicists in the audience, look out. When you look at books of logic and model theory, advanced logic, you will find something called formal semantics, which is really the legacy of Hilbert, in which you investigate the mathematical consequences of assigning arbitrary meanings to words, and specifically arbitrary extensions. So there's a difference between intentional semantics and the practice of logic and model theory. Anyway, in this framework, we've got a natural understanding of what is a subject matter. Namely, it is a partition in the mathematician's sense of the set of worlds. That is a division of the set capital W into mutually exclusive and jointly exhaustive sets. So W is a union of subsets that do not intersect. Those subsets are called the cells of the partition. Why is a partition a good example of a good way of thinking of a subject matter? Well, think of a subject matter as, I don't know, the 17th century. So whatever happened in the cosmos during the 17th century, well, ways the actual world could be, could differ in countless ways outside the 17th century, while agreeing on everything they say about how history unfolded inside the 17th century. So two such worlds would match as regards the subject matter, the 17th century, but they're not the same because they differ in other respects about history before 1600 and history after 1700. So two worlds can match as regards the subject matter, and you can gather worlds under the equivalence relation of saying the very same thing about the given subject matter. And the equivalence classes of worlds under that equivalence relation are exactly the cells of the partition. So a proposition will be entirely about a subject matter if the set of worlds in which it is true is a union of some cells of that subject matter. Okay. And the same goes for conjunctions of propositions, and I'm going to take theories to be conjunctions of propositions. And with this framework, we can now make precise the idea that two dual models are about distinct but isomorphic subject matters. The idea is that we have model triples, they are theories. We have two of them, they are duals to each other. Each of them is perhaps false, perhaps true in the actual world, but each of them is wholly true at certain worlds, in fact, wholly true at many worlds, namely at a set of worlds that is a union of the cells of the partition of that subject matter. But two dual model triples might have partitions that are different. And so therefore are the two dual sets of worlds where each of the two duals is true. So the sets are distinct. The duals do assert different propositions, but the two sets need not be disjoint. and both of the model triples could be wholly true. Okay, so to sum this up, let me introduce labels, which are a bit ugly, but they are easy to remember. There's two ways that two dual theories can differ or disagree or be different. And this contrast between the two ways, it doesn't depend upon the word duality. I mean, this is just true about any two theories or any two long conjunctive propositions. They can disagree by having a common topic, having a common subject matter, but making assertions about it which cannot both be true, or as we put it in brief, they contradict each other. But that you can also differ or disagree in what you might call a milder or more happy sense, namely, they have different subject matters. One proposition is about sugar, the other is about salt. They differ, two such propositions differ, but they can both be true and they do not contradict one another. So in the case of dual model triples, contra for contradict would mean two unions of cells of a common subject matter, the two unions are disjoint. Whereas diff, where diff stands for different, the two dual model triples are wholly true at distinct sets of worlds, but the sets of worlds are themselves drawn from two different partitions which cut across one another. But the sets needn't be disjoint. They could overlap, and the actual world could be in the overlap. But they differ in the sense that the sets are distinct. Okay, so this is the end of my second part, right? The intentional semantics. And if I may, I'll invite discussion or questions or comments on what I've said so far. Okay, would anybody like to comment? No?
Well, actually, Jeremy, I'm waiting for your examples to step
Okay.
in. So
thank you.
Yeah.
Right. So we go on. Here are the examples then. Simple examples. The first one that I promised is Newtonian mechanics. But there have got to be two theories or models. So I wish to send you back to 1687 with the concept of absolute rest, Newtonian mechanics as it was first understood and first perhaps learned by you. Imagine different specifications of what is the absolute rest, which differ by a boost. So, of course, all this is associated with a Galilean group velocity boost in some specified direction at a certain specified speed. Let it be the x direction at a speed little v. So I want you to imagine two formulations of Newtonian point particle mechanics. For example, capital N particles which interact by Newtonian gravity, but these formulations differ in what they identify as absolute space. There is a disagreement between them about what, as we would say in the modern language, what inertial time-like congruence in space-time is truly at rest. So there's a space, in modern language, there's a space-time R4, and the bare theory would be what we now call the neo-Newtonian or Galilean space-time, with point particles inhabiting it subject to Newtonian gravity. So that would be the bare theory. And if we want to ask about the model triples, well, the specific structure, the thing that's making them different one from another, is of course the specification of absolute rest. And the left dual might specify as absolute rest what, if we have the structure R4, is the mathematically obvious congruence. The lines t, x, y, z, where t varies, but y, x, and z are all fixed. Those are the vertical lines in the obvious picture we draw. On the other hand, the right dual specifies that rest is really the congruence of lines all parallel, all straight, but tilted, going off to the right, upwards. So I've invoked the vector space structure of R4, preferred origin, and so on, in order to say this without talking fancy differential geometry about charts and rubbing out the preferred origin by talking about affine spaces. But that's just to keep it simple. There's no need for the mathematical abstraction. Is clearly, you can imagine, two people who make different specifications of absolute rest. So I'm thinking of them on the left and right, and they differ by a velocity boost. So in terms of the duality maps, a state is in fact an assignment of positions and velocities to each particle. And the duality map on states will take a state on the left dual to a state on the right dual. Now, here, this philosopher's constant preoccupation with what is same and what is different becomes vivid again. The duality map is going to preserve numerical values. That was the condition of equation 4, but it changes the physical state from the point of view of participants on the two sides who take themselves to be disagreeing with one another, because the numerical values on the right are numerical values with respect to the right model's concept of absolute rest. So a philosophy and history remark about this example is, it's tempting to say that these contrary specifications of absolute rest are, or they're really a distinction without a difference, or they're gauge, or they are a sign that we should really move beyond these formulations to a neo-Newtonian formulation in which the surplus structure is eliminated. Well, it's certainly tempting to say those things now, but my point with this example is that these are temptations that we have due to historical hindsight. We now know, thank you, Cartan, the neo-Newtonian formulation. But if we returned to 1687 or 1750, or even 1850, these views are tenable. And the duality in that sense illustrates what I call contra, right? I'd remind you, it's not on the slide, that when Maxwell found that the observed speed of light was encoded in his equations as the speed of propagation of the wave-like solutions of his equations, and he then made this amazing identification of light with electromagnetic waves, he immediately began to suggest ether drift experiments to detect the motion of the Earth with respect to the ether, because there was now a putatively fundamental theory, Maxwell's equations, in which a speed was given, which was not true in Newtonian mechanics, of course. With F equals ma and the Galilean transformation, speeds are transformable away, to put it in rough terms, by a velocity boost, but accelerations are invariant. So when Maxwell did that, he was reflecting the natural thought that the specifications of absolute rest represented a conflict, and that one could determine by invoking electromagnetic phenomena which specification of rest was correct. Okay, so I do agree, and this goes back to Sebastian on heuristic functions and practical roles of dualities, that these temptations hint at how a duality can prompt us to guess what the bare theory is when we don't have a formulation of it. And sometimes, when it's not a matter of finding a common core or bare theory, the two duals might be not really, the two theories might not really be isomorphic copies of a bare theory, but they might be approximations to it. And we might be helped to formulate that theory by being faced with the two models. So that was contra. Here's an example of diff, right? An example of simply having different subject matters. Let the bare theory describe a quantum particle confined to a line. So the states I'll take to be wave functions, to keep it simple, rather than the members of an L2 space. I'll write it as just psi as a function from the real line to the complex numbers, but officially the state space is L2 functions, which are equivalence classes of wave functions. On this space, we can take the quantities as all the bounded operators, fine. So the theme for this slide and the next is, think of the left dual as about position, think of the right dual as about momentum. When we study quantum theory, it's usual to think of these choices as just choices of basis. A wave function is mapped by a unitary map, F for Fourier, to its Fourier transform, itself a map from reals to complexes. And the usual representations of position and momentum in the elementary, most familiar representation are in fact related as Fourier transforms of one another. So it's not just the states that are mapped by Fourier transform, but this unitary map F is intertwining the position and momentum operators, as you see in the equation. Well, this is normally regarded as a change of basis, and expectation values are invariant under a change of basis. And that is because they're calculated from an inner product in an inner product space. So this is a prototype of the left and right duals not differing. This is agreeing, describing the same physics, as physicists would say, but in surprisingly different terms. Somebody might have their entire understanding of quantum mechanics cast in terms of position without knowing anything about momentum, or vice versa, but they've got access to the same wave functions, and the state is fully described by the state considered as a position wave function. And bosonization, which Sebas talked in detail about, is another example of what you'd call the same physics described in different terms, again, with a unitary equivalence. But I want to give you an example of diff, and we can get an illustration of it by, in the same example, by thinking, so to speak, like Niels Bohr. I want to, it's less subtle than Bohr, but it's got the same spirit. The idea is there's a position perspective, there's a momentum perspective, but you cannot adopt both of them together. So I want you to imagine then, on the left, there is what I will call a monomaniac about position. This is a person who wants to interpret the formalism only in terms of position. The states are probability distributions for position. That is to say, the mod psi squared functions are probability densities for position. And on the left dual, the quantities are to be just position and its functions. like position squared or polynomials in position, and their expectation values are calculated in the obvious way, which you see at the end of that paragraph. On the other hand, on the right, there is, if you like, a person who thinks of the physics wholly in terms of momentum. The states are just probability densities for momentum, and the expectation values of functions of momentum are given in the corresponding integral. So for this situation, the duality map will actually be the identity map on mathematical functions. It's not the Fourier transform. It maps a function to itself, but the argument function is taken as interpreted in terms of position. The image function is interpreted in terms of momentum. Okay, so that's diff because it's different partitions. Okay, we can discuss this, how this relates to Bohr later on, and we can also put this in more abstract terms, of course, about different choices of the abelian algebra of quantities that the two duals are focusing on. Okay, so here's another perhaps more vivid example, more plausible example of diff. This has more algebra in it. It's Kramers-Vannier duality in classical statistical mechanics. So it's an example, I say, of my different subject matters. The Baire theory is the classical equilibrium statistical mechanics of a two-dimensional square lattice. Think of graph paper. There's a certain Hamiltonian which governs the energy associated with configurations of up and down at each site in the lattice, plus or +1 or -1. And the energy is lowered by having neighboring sites having the same value. So as people always say, the system likes to align the values at the sites, and the word spin is always used, even though actually this is a classical system, and it's only spin in the sense that it's a binary or dichotomic quantity with two values, up and down, or plus and minus, or plus and -1. But for a configuration S, which is an assignment of +1 and -1 to each site, the Boltzmann probabilistic weight for a configuration is given by this famous Gibbs-Boltzmann formula of e to the minus beta h of the configuration S, where beta is 1 over Boltzmann's constant times the temperature. So that's the Baire theory. The duals are approximations to this full theory, which express the partition function, some of those Boltzmann weights, in a way that is valid at low temperatures and at high temperatures. So the dual models aren't the full theory. They are roughly homomorphic copies of the full theory, one for the low temperature regime, one for the right temperature regime, and they pick out as their overarchingly important quantity the partition function Z. So we in fact write this partition function using the Greek letter nu, which is a dimensionless inverse temperature. Capital J is the strength of the coupling between sites, and it's convenient to define nu star by this formula that it's tangent to the -1 of the exponential of -2 nu. The point about that is just that nu star is 0 or infinity when nu is infinity or 0. So that a low temperature, which is a large inverse temperature nu, will correspond to a high conjugate temperature, that is a small new star. Okay, so there's a flip here, not just between capital T and beta, but also between nu and new star. And the second flip undoes the first flip. Low temperature is small new star. So think of new star as the dimensionless temperature. When the lattice is cold, new star will be small. Okay, so the crucial point is this statement that relates the partition function expanded in nu and in new star. Capital N is the number of sites in the lattice. And that relation is in effect all the soul or the meat or the core or the kernel of the duality. So if we want to put it in terms of Sabas and my schema, take the left dual to be the family of expansions of Z parameterized by the temperature T being in some low range. So left dual will be cold lattice. So it will be large nu, large inverse temperature. And the right dual is the expansions parameterized by a small new star. And there should be a -1, I'm sorry, range tangent to the -1 of exponential, tangent to the -1 of exponential. Okay, so whoops, the duality map then is, gone back too fast, excuse me. The duality map is mapping from Z nu to Z nu star. And as it's written there, the low temperature regime and the high temperature regime are different, but the formula is corresponding, and we can talk about an isomorphic piece of physics at low temperature and high temperature. But nobody would say that there is no real difference between these duals, or that the contrast between them is gauge. Right? It's a straightforward bit of the same formulas in two different regimes. Okay, so those were my three examples, and we now have a more philosophy comment about what this means for the philosophy of theoretical equivalence. But I'm going to just pause in case there's a question or comment. So I invite comments now, if anybody wants. Yeah, well, Pedro, would you like to go ahead, if I'm allowed to be my own chairman?
Yeah, if it's okay. I mean, so just thanks, Jared. I mean, this is just a comment. I was I was waiting for your examples because I'm having a hard time. I mean, with basically the idea that a duality may be an instance of contradictory subject matters, and the example that you gave, I mean,
Yeah,
of absolute rest, I mean, I'm having a hard time because thing is, as you rightly said, I mean, Maxwell, I mean, then of course, in his theory, I mean, put forward a way basically to perform an experiment in order to vindicate or refute this absolute rest. But the thing is that this celebrating Microsoft model experiment in a, of course, technology penny, I mean, might have been performed in Newton's own time. So the thing is that, as you know fairly well, I mean, in Newton's own time, there were this controversy with Leibniz and so on. So the thing is that I can't say that basically the issue of absolute rest is basically a topic of two dual theories. in the sense of contradicting each other, because I mean, there is a way to basically go either of the duals of, well, these square dual theories. And okay, and the other was vindicated empirically, of course. Well, it took over a century to do so, but was just a matter of contingency, historical contingency. The thing is that it's hard for me to basically fathom, I mean, the idea of a duality between two theories, and the subject matter being contradictory in itself.
Right. Well, I think, let me say two things, if I may, and see if it makes a bit of peace between us. I mean, one comment is I completely agree with you that the Michelson-Morley could have been done in 1688, and that there was a resistance to Newton's idea of absolute rest because of Leibniz's relationism. And I'm very sympathetic to, like you were saying earlier in discussion on Zoom, about being sympathetic to Markian and relationist foundations of dynamics. So even in 1688, it was sensible, or even more than sensible, it was wise to say absolute rest is not a real physical quantity. It is an artifact of 1687 book, but it ought to be disposed of. So I'm quite sympathetic to that. But I just wanted to give what you might call a dogmatic Newtonian example that was simple. Well, sorry, I wanted to give an example that was simple of how our schema can relate to things which, when you interpret them, do disagree in that strong contradiction sense. I wanted to do that. Okay, this is my second comment. The schema is formal. It talks about isomorphisms of maps and that preserve values of quantities, but it doesn't say whether the quantities are silly or good, right? And the way you should interpret the thing on the left and the thing on the right. And in that sense, this is my second comment, you can see my pedagogic intention. I wanted to emphasize that the schema is formal, so that although it is a mathematical meshing, that mathematical meshing does not mean necessarily agreement about claims about the world. It could even be a case where there is disagreement about claims about the world on the two sides, even to the extent of contradiction. But I do agree with you, and Sebastian may want to comment on this, or I certainly think we said this a bit in the papers. Almost nobody now uses duality when there are cases of two theories which on the two sides are regarded as contradicting each other, literally disagreeing in that strong sense. So one could adjust the definition of duality from what we did, but it does bring out that our schema is formal. It's not about interpretation. So it tolerates examples where on the left and on the right, they literally contradict each other. And then, of course, I wanted to give a simple example. I hope that helps a bit.
Yeah, it certainly does. Yeah, so okay, yeah, thank you very much. It certainly does. I mean, I don't want to take up too much time and distract your.
Okay, thank you. So now, is there any other question or comment that anybody'd like to make now?
Maybe just a quick question. So one thing that seems quite interesting about these examples that you presented is that in all these cases, it seems that, in a sense, the ultimate fate of the duality was to simply be resolved inside a common core, but very physically salient representation, right? So it seems that when you think of the Newtonian mechanics example, you actually said we should try to resist to get this example, the temptation to move to near Newtonian space-time, and the same thing with position and momentum in quantum mechanics, where it is simply, today they are seen as simply two different bases. At the same time, it seems that if you take some of the more contemporary examples, even if you take just the simplest one, something like bosonization, it seems that we do not have such a physically compelling story to tell regarding the common core. It seems much more abstract in a way, what we can say about the common core. So I was wondering if in your mind there is anything that maybe you can add to the scheme or whatever, any principle that can help us distinguish, or if it's just a historical accident that can help us distinguish the cases where it seems that the duality in a sense is a signal that we should just remove the extra structure, and from there we get a more physically salient representation for cases where it seems that, from cases where it seems that the common core is more of just a mathematical structure rather than a very compelling physical structure in the way that Hilbert spaces or Newtonian space-time is, maybe.
Yes, I apologize. Actually, I can't quite hear the question. I know the question is asking, can I say something about the cases where it is either easy or important, or perhaps, you know, one but not the other, to go to the common core from the duals, compared with cases where it's very difficult or not important? Is that the question?
Kind of, yes.
Yeah. I think I don't have any helpful comment. Sebastian may have a comment. He may have heard the question better, but I don't want to force him to speak.
I don't have much to say at the moment. Happy to discuss later.
Okay. Thank you. Yeah, I think it's rather like the answer to Pedro's question. It brings out that our duality is quite our schema is formal. So there is not much in it in detail with which you can articulate when is specific structure suspect and should be disposed of, compared with when it is not suspect. You won't get that in words of the generality that we use when we present the schema. You only see it in examples when you can make a good judgment, I think. So I'm sorry. But anyway, so that's the situation. Shall I march on? Because it's getting late. My understanding is that we have about half an hour altogether from now.
Kind of, yes.
Yeah. So before I talk about emergence, here is a perhaps amusing implication of the discussion so far for people in philosophy. There is a recent literature about theoretical equivalence. When are two theories equivalent? In fact, Sebastian touched on this in detail with authors like Weatherall, Barrett, and Halvorson. And they are interested in saying, well, logical equivalence of theories is the traditional core notion used by logicians and model theorists and people in so-called formal semantics. And they often say it is too strong. Let us find something weaker, which covers cases that logical equivalence excludes. I want to make the contrary remark, that logical equivalence is sometimes too weak, and dualities provide examples. Two dual theories that satisfy either my contra or my diff could get formalized in such a way that they end up being logically equivalent. But no physicist or scientist thinking about them would call them equivalent, because the word equivalent, as normally understood, makes the same claims about the world. So I want to exhibit to you how logical equivalence is in that sense too weak. There will be cases of theoretical inequivalence, which are going to get classified as logically equivalent. And this criticism that I'm about to make of logical equivalence will, of course, apply to anything that is even weaker. So my comment now, I claim it is worth stressing because the recent philosophical literature on theoretical equivalence, Barrett, Halvorson, Weatherall, has been saying logical equivalence is too strong. And I agree, there are cases where two theories are cast in different languages and clearly make the same claims about the world. I mean, even a baby example, classical electromagnetism written in English or in French, right? So I'm emphasizing that there's a problem in the other direction. And in short, therefore, whereas the traditional, well, the literature of the last 20 years thinks of synonymy causes a problem for logical equivalence, I'm saying homonymy also causes a problem in the other direction. Homonymy meaning two words spelt the same way with different meanings. And now let's call the person who advocates the left dual Alice and the one who advocates the right dual Bob. But just imagine that Alice and Bob are unfortunate or unwise. By coincidence, they use the same words when they advocate their theories, and an appropriate subset of their words have been inverted in their meanings so that they say out loud the very same words, even though their theories disagree. In that way, their theories could even be formalized so as to be logically equivalent. So, for example, in the last Kramers-Varnier duality, let Alice be like me, she speaks standard English. And in advocating her expansion for the icing lattice at low temperatures, she says words like low temperature expansion. But suppose that the semantics or the intended meanings of Bob's language is inverted compared with Alice's in a high-low way. So Bob is trying to describe a hot lattice. He is advocating the right dual, but he says the word low temperature expansion in order to describe his partition function. So they're advocating different theories, but they might say the very same set of sentences. And that's the comment. I think to have more discussion, and because it's late, I won't make a big deal about this. You've seen the point that there could be this unfortunate change of meaning, which means that people who wish to say different propositions about the world come out uttering the same sounds. So that is spelt out in this first half of this slide that you see on the screen now. Alice describes a state, which is the partition function in terms of nu. Bob describes the transformed state, which is the partition function in terms of nu star. they're saying different assertions, but their assertions are compatible. It's what I call diff rather than contradiction, but they're actually saying the same words. And in the same example, and in the other examples as well. In the second example, imagine Alice speaks standard English, her word position does mean position, like mine. But on the other hand, poor Bob on the right uses the word position to mean momentum. They might come out saying very different propositions, but uttering the same words to say it. Right? So it's again a case of diff, which is hidden by their logical equivalence. Now, this slide simply makes the comment that if we then seek something weaker than logical equivalence, the same line of thought will equally apply, because having said, logical equivalence is too weak, it will follow that I'm committed to anything weaker than logical equivalence is also too weak. And one thing that is weaker than logical equivalence is what Gleamore in 1970 brought to the philosopher's attention, which Sebas on, as I recall, Wednesday discussed. It's this definitional equivalence, or having a common definitional extension. And we simply comment that introducing this weakening of logical equivalence will make no difference to the line of thought that I have been urging on you. And the reason is the logical framework deliberately sets aside intended meanings. Okay, so we can come back to that in discussion if people want. My final comments then are about emergence. As I said at the beginning, emergence is a vague and even controversial notion. And I like Sebastian de Haro's account in European Journal for 3 years ago, in which ontological emergence involves two things, two theories. One is emerging from the other. It is called the top one. The one from which it emerges is called the bottom one. So there's little b and little t in the subscript, and there is some sort of map or relationship between them called link, from the top-bottom theory to the top. The physicist can think of coarse graining as the standard procedure by which you might get the top theory from the bottom. You look at a small minority of the total set of observables or quantities, and that's just linkage, if you like. But for emergence, or emergence in a strong sense of ontological emergence, which is the topic of de Haro's proposal, the domains of interpretation should be distinct. So capital D now for domain, and that is a part of the world. It's not a theory, it's a sector of reality. And the idea is there'll be sectors of reality truly described by top theory that are not contained in bottom theory's description. So in that sense, the linkage map is not as simple as just throwing away information and saying less. There's something novel or ontologically emergent about what's happening at the top. Well, how does that relate to dualities? Well, one can imagine that there are two duals, left and right, and that there's top and bottom distinction, and as in the figure, there could be such a case, perhaps. And actually, we will see such cases. And in fact, going back to our contra and diff, examples of contra and of diff will illustrate that commuting diagram. And they will also illustrate that diagram does not contain the assertion that top domain is not equal to bottom domain. That is an extra assertion beyond the commutation, but we will see examples with ontological emergence and examples without it, so that's fine. So this is really a curious exercise, of having to adapt our previous discussion to a top-bottom contrast, and is there an ontological emergence? Is the top theory's domain different from the bottom theory's domain? So there's several binary contrasts in play in this discussion. There's obviously the left and right of duality, but there's also the top-bottom of emergence. And there's also the question of, is there ontological emergence in the sense that the domain is of the top is different from the domain of the bottom? And there's the contra-diff contrast. So let's go back to contra with asking Pedro's forgiveness for having calling this a duality, even though there is an agreed mutual contradiction between the left Newtonian mechanics and the right Newtonian mechanics with rival or mutually contradictory absolute rests. So what I want you to imagine is that what we had 20 minutes ago are top theories, but we have now discovered non-relativistic quantum theory, and it is a bottom theory set in Newtonian space-time. It also can be envisaged as having left and right formulations, and they differ by having different absolute rests, and they are dual by a boost map, which is exactly the Galilean velocity boost transformation on states and quantities. So there will be a dual at the bottom, D sub B, moving one quantum theory to the other. So this all works neatly. We have the commuting diagram because the boost concept, of course, is in effect the same in the quantum theory and the classical theory, though as students of quantum theory will know, like a bit beyond the first textbook, Galilean quantum theory is a subtle business with phase factors added under Galilean transformations that you, of course, don't see in the classical case. And it is true, I would say, I hope Pedro will forgive me and go along with this, that at the bottom theory, again, we do have contra. I mean, this is a conflict of the two theories on the left and right about what is the absolute rest. But the link map, the upward link, is something like H bar goes to 0, or whatever you believe defines the emergence of the classical from the quantum. So there's a link on the left and there's a link on the right. They'll take essentially the same form, because everybody believes that the story of the emergence of the classical from the quantum is not affected by a Galilean boost transformation, right? So most people would say that, gosh, classical and quantum are so very, very different that if the classical world emerges, it should count as ontological emergence. So the domain, capital D notation, will be registering as different domains. In any case, that issue of whether there's ontological dependence has no relationship really to whether a boost has been performed. So either both link maps give ontological emergence, which most people would say, or both do not. So that's putting Newtonian mechanics at the top and asking for a quantum underpinning and its relationship to duality. We can play the same game putting Newtonian mechanics at the bottom. So our example we're now familiar with from half an hour ago, right, left and right, two Newtonian point particle theories, rival absolute rests, dual by a boost map. They're now the bottom theory. So there's going to be something above, which is something like coarse graining. And let's take the simplest sort of idea. Let's simply do exactly that. Let us coarse grain. Let us define the motions of the center of mass of the capital N particles. Well, these little mini theories will be dual by the boost map on states and quantities upstairs on this very logically weak theory that only talks about the motion of a single degree of freedom, the center of mass, or if you prefer, center of mass and a few other collective variables. Again, these link maps, most people would say, do not give ontological emergence. They're just at best epistemic emergence. I mean, it is just summary information in terms of a small set of quantities, such as center of mass. In any case, the issue has no dependence on a boost. So the debate goes through one way or the other on the two sides of the duality. And the top theories illustrate contra, just like the bottom theories did. Okay, so final two slides then. We can play the same game with diff. So far, we've kind of walked through a case of contra, Newtonian mechanics. Now let's take a case of what I called diff, namely logically compatible assertions by the two dual theories. So I'm going to put them at the top in the first slide. I want you then to go back to what I called the monomaniac position and momentum theories on the left and right. Let's talk about Alice and Bob. Alice is a position monomaniac. Bob is a momentum monomaniac. The two theories are dual by the duality maps that we discussed. But now I want all this to be on the top row. Everything we said before is to be at the top of an emergence relation. On the bottom, let us imagine monomaniac colleagues about position and momentum who are advocates of the pilot wave. So pilot wave Alice at left bottom does use a pilot wave state with possessed positions x1 to xn added to the quantum state psi, but she only does that in order to extract information about probabilities of position. On the other hand, sorry, there's a misprint there. It shouldn't say TL sub T on the left, probability density for momentum. It should be, of course, TR sub B does the same for momentum. They're dual by the obvious duality maps, the ones we had before, just with the treatment of the particle positions as part of the quantum state, part of the notion of state at the bottom. And the point is that the duality map is really regardless of whether or not you believe in particle positions in the manner of the pilot wave theory. And this link would be simply dropping the particles' positions. And most people would say this is not ontological emergence. This is epistemic emergence. If you advocate the pilot wave, you do not believe that orthodox quantum theory can claim such kind of novelty as the word ontological emergence suggests. And this, of course, applies on both the left, position quantities, and on the right, momentum quantities. And on the other hand, final slide, one can put the monomaniac position and momentum theories with which we began at the bottom, and one can define a link which is really a matter of coarse graining, like let us only consider the motions of the mean of the distribution, or the motion of the mean and some other statistic. And then one will have what I was calling mini theories at the top about such a small set of variables such as the mean. And there will be the mean of position on the left and the mean of momentum on the right. They will be dual by the usual position to momentum map. Most would say that this is simply epistemic emergence. But in any case, we have a case of diff. There is no contradiction. So thank you. There is a lot about symmetry, which I'd like to skip over and simply say mille grazie. Thank you.
Thanks a lot, Jeremy. So we have roughly 10 minutes for questions. So you can either raise your hand or
right.
Chat.
So I'll stop sharing now. Yeah.
Yes. So Sebastian has a question.
Yeah, so that stuff about emergence, I thought it was interesting that so in these examples that you showed, if I understand it correctly, what you're saying is that the emergence map preserves the property of either contradicting each other or saying different things. So my question is, so you showed this in these examples. Is this something general, or does it just happen to be preserved in these examples?
Sorry, what exactly did you say is being preserved or not preserved? What was the topic?
So I thought, if I understood it correctly, I thought you were saying that when you have duals that, for example, contradict each other,
yes,
and you apply emergence along a given direction, then at the top and at the bottom, they both remain to contradict each other. So by emergence, you never go from a situation where they are about different topics to where they contradict each other or the other way around. Is there an underlying reason for this, or does it just happen to be?
Yes. I think that broadly, contradiction between them could be lost if they are at the bottom and one is moving upwards to the top, because broadly, upward movement can be logical weakening, for example, by coarse graining. And contradiction can be lost when the two people debating or the two disputants weaken their positions, right? They both, as we would say in ordinary conversation, they just withdraw from some of their opinions, and they might come to agree on their revised, logically weak opinions. I'm so sorry, I'll just have to turn that off. Telephone from the electrician trying to mend the house. On the other hand, downward, contradiction would be maintained in general. If we've got contra at the top level and we're looking at what's going on at the bottom, I would expect contra at the bottom because of this general way that the upward flow in the diagrams is a logical weakening. I hope that helps a bit. Yeah.
Was that the hand, Michael?
No.
Oh, so answer the question?
Yes. Thank you very much, Jeremy, for your wonderful presentation. So I understood that in your opinion, duality is a phenomenon also before electromagnetism. I thought before that duality between magnetic and electric field was the first case in physics, but you show also a case in which in classical mechanics, I understood that if one assumes the existence of absolute space,
Yes.
as it was made by Newton, it is possible to imagine dual situation from a logical point of view and a physiological point of view, very similar to what happened in electromagnetism, quantum mechanics, and
Yes.
okay.
Yeah. Thank you. Yes, I think I'm very grateful for the question, and I do agree with you. And I think just to add a little detail, it reflects how Sebastian and I formulated the schema. Namely, it is a quite undetailed, logically weak schema, and it is quite formal. And so it's not so surprising that something like mechanics might exhibit it. It's also, as I was saying, this allows it to have examples with contra, what I call contradiction or contra, and it has examples which are not of scientific interest. I mean, the different specifications of absolute rest were of scientific interest and debate in the foundations of mechanics, but it's relatively simple to understand what is going on, even though, you know, geniuses disputed what is the best view, but it's not intricate and it makes no difference to empirical predictions. But you have spent the week studying advanced examples where there was a real scientific interest, and this is not part of our definition of duality. So I had the easy job this week, which was to say something about the broad philosophy, and not to.
Jeremy, sorry.
Yeah.
Jeremy, the internet went down on the room. If you give me a second, I restore the connection.
Oh, okay.
Went down midway through your answer. Sorry.
Halfway through this. Okay.
Yeah.
I am really saying I agree with.
Oh wait, can you just wait a second, because I'm talking to you from my laptop, but there's no microphone or anything powerful enough.
Right. Okay.
Second, I'll just try to restore everything.
Okay. Okay. Can you hear me now?
No, wait. I don't know why it's asking me for. Why is it doing this? Hmm?
I'm very happy to just turn off and launch Zoom again, if that would help.
Recording in progress.
Okay, we're back home. Can
We're
you
okay.
Sorry?
Thank you. So
Yeah.
you can hear me now?
Yes, we can.
Okay, thank you. Well, what I was saying, I make it shorter now because it's been a very long week and long day for you. But I agreed with the question that yes, the examples in mechanics that I advocate in the talk are relevant because they illustrate the schema. But this is more because the schema is simple. The schema does not try to demand that a duality has scientific detail or easily observed content or weak, strong coupling being related to one another, the kind of thing that Sebastian discussed. So it is really the simplicity of the schema as defined. But in the paper which is cited on the title page, I do give another more deep example of duality, which is the Legendre transformation. That also counts as a duality in the sense of the schema. So it isn't just that I can find as a rather artificial example in particle mechanics. There are really deep ideas which also illustrate the schema.
Yes, yes, the Legendre transformation is also a very beautiful example. Yes, yes, all right. Thank you very much.
Yeah, thank you.